All right, hello again, everyone. And I will again ask you if you have any questions from previous lecture. Now is the right time to ask if you want. No questions. Okay, if you want to discuss even homework, now is a very good time. All right, no questions. Let's go then to the topic for today. It's Canonical Ensemble. Okay, I'm reading. Canonical Ensemble. Canonical Ensemble. Now I want to recall this picture that we already started drawing last time. Now I'm considering a super system with a small system inside. Okay, thus the super system has energy capital E. No, sorry, that would be column. Subsystem, system of our interest has energy epsilon. Okay. The rest of the system, or the rest of the super system, which is the super system with the subsystem, with the system of interest excluded, we can call heat bath or heat reservoir. These are synonymous words, terms in statistical mechanics. And why I tell heat bath or heat reservoir, as we agreed last time, we consider such interactions in which a number of particles in N and V in the, so number of particle volume in the reservoir remains constant, as well as number of particles lowercase n and lowercase v in the system of our interest also remains constant, but energy can be exchanged between heat bath and the system of interest. All right, no questions. Then we proceed as follows. We already have defined what is entropy of a macro state, and we want to find the entropy of a given microstate, of a macro state at which the system has energy epsilon. We assume that the Boltzmann rule applies, right? That it's a logarithm, a constant of Boltzmann times the logarithm of the number of microstates that realize this macroscopic configuration in which epsilon is the energy of the system of our interest. Now we use a very frequently invoked theoretical trick. We use the tailoring expansion. Last time I began asking Ivana to reproduce this. Actually, if you have read the notes that I sent you in statistical mechanics, you will always need sort of approximations, because we study really complex systems. It's desperate agenda if you approach everything with exact calculation. Often to study complex systems such as biological cells or something, or economic agents, other various aspects of life sciences. Such systems are so complex that you must be really inventive and cunning, I would say, to come up with interesting and useful approximations. And the Taylor series is a very old trick in the physics in general. Just to remind you, for instance, the Hooke's law, we used it last time to describe a spring. It's also, in reality, a Taylor expansion. Okay, so let me ask Anna. So can you expand in Taylor series? So we consider epsilon as the variable of our interest. Can you expand in Taylor series the entropy of Sm of capital E minus epsilon?
Okay, is the summation? I don't know how to say it in English. Yes.
Yes, let's go term by term. Name me each term in this summation. What is the first term?
The n, okay, derivative.
So we want to use this point as a point of Taylor expansion, okay?
Okay.
So first term should be?
Sorry, because of the noise. The first derivative, bueno, the derivative, the first term?
Yeah,
okay.
The very first term, I write?
Is SE?
S, yeah, of macroscopic state. Okay, let me then, for simplicity, to remove this subscript. S of E, yes, S of E, okay, and then?
Plus.
Okay, plus?
The first derivative.
Okay, the first derivative, let me write it as, because you remember I have omitted the dependence of entropy on number of particles and the volume. I write only energy because for simplicity and brevity. Then that's the reason why I'm going to use partial derivative sign. So it's with respect to?
To E, I don't know how to say, epsilon?
Epsilon, right, epsilon.
And that's epsilon.
Okay, what? Time?
By times E minus epsilon.
This is the point of expansion, right? We don't expand them. So what you're telling me would be right if the first term would be S at
Shouldn't it be partial S by partial E?
So we agreed that we agreed last time that supersystem is a microcanonical ensemble, which means that E is fixed, okay? So I'm using this value, epsilon, as a variable.
No, but our variable, what is our variable?
This is epsilon, I'm telling. Variable
so it should be E, it should be epsilon into the first derivative of S with respect to E then.
Well, so far is almost correct. It's almost correct so far, I must say. Okay, almost. We didn't finish the expression.
I have a suggestion. I don't know.
All right. Okay, let's ask Dionys. Is it right? Who's talking? I'm sorry, I just don't see. Ivana?
I think it was Ivana.
Ivana. Oh, okay. Ivana. Yeah, I'm asking because I'm not always seeing who is responding. Ivana, tell me.
If you are considering epsilon and the term and must be minus instead of plus.
Yes, that's correct. Yes, that's correct. That's why I was telling that it's almost correct, because there will be minus and.
Yeah.
That's all?
Yeah.
So this is entropy. This is the. No. This is entropy, units of entropy. This is entropy divided by energy. Units of entropy divided by energy. What is missing? We cannot sum units of entropy. Huh?
The entropy in the point in entropy as a function of E.
No, yes, this is right. Evaluated at E. Okay, that's correct what you're saying, but it's not enough because you see, Boris wants to answer. Times
E
E
minus
minus.
So you are trying to do that, okay? But then I tell you, what if I want to use expansion of entropy around a value 0, right? S at 0 would be epsilon equals S of 0. Then I would put here, then there would be ds. Yeah, that's a common thing, that you start to think about expansion about Maclaurin series, expansion about 0. And then I would put here, sorry, epsilon. So you see, that's not just all right. This expression is not correct. All right.
Yeah.
Yeah.
Invest.
Hey, oh, yeah. So what I suggest, sorry, okay. I suggest you to check Taylor expansions. Probably you will do this in your math course now, the crash course that you have now on math. But what is, so to correct this expression, it is simply times
Epsilon minus E.
It's just epsilon without E, okay?
Yeah, it just epsilon.
It's just epsilon.
No, wait.
Okay, because yeah, so when you have a function of x, okay, let's recall the function of x expanded about point x naught. What is it? It is f of x minus plus d. Yeah, I will omit all terms which go as power as the order of epsilon squared. D of dx, okay, or f evaluated at x, x naught times x minus x naught. Now I tell you that now I'm putting here variable r, which is equal x minus x plus x naught, right? So no, something is not right.
No, that's it.
Yeah.
That's it. Because the minus sign come from minus epsilon.
Yeah. From minus epsilon. That's correct. Yes.
Just like we are putting that x is e minus epsilon and the x0 is the e. So for x minus x0, it is e minus epsilon minus e.
Yes. So basically, right now we are substituting. We need to substitute. So something that. So here the expansion is e, but also there is inversion. Basically, we call this as minus epsilon. Okay, this thing is minus epsilon. Okay, this is e. And then to find x, okay, so if this is epsilon, then x equal, if this is minus epsilon, then x is x naught minus epsilon, you see?
Yeah.
And then here we have x naught minus epsilon. Well, x naught is e. So it's a little game with the arguments. You should get a little more fluent with the Taylor expansion. Okay, so this is correct Taylor expansion, and we omit terms which go as epsilon squared. Why? Because we are considering very large system. So suppose that this is the heat bath is the size of universe, and this little system is a cup of coffee on your table. Okay. In that case, this E is huge, how much energy there is in the universe, but epsilon is a very tiny number. Therefore, these orders we can neglect. All right, is it clear? Okay.
So
Yes.
why we use the Taylor expansion for the entropies in this case?
Well, that's because I'm going to derive canonical ensemble. Right now, you know what is microcanonical ensemble, and trying to do a theory of supersystem as a theory of universe is also a very complicated task, right? We are not going to write the theory of universe. What we usually interested is in small system which is connected to a larger system, but we know we can measure and operate with variables inside the system. And for that reason, we are going to derive a more useful concept, canonical ensemble. Okay, so it's a canonical ensemble will be a system which can exchange energy with the environment. All right, to derive it, we start with the expression for entropy. That's the first step of derivation of canonical ensemble. Okay?
Okay, sir.
Then, number of states. Okay? Number of states when of the super system. Okay? Number of states of the super system when the whole the super system has energy, the heat reservoir has energy E minus epsilon, and the system has, so this place is the energy of the system, okay? So let's recall, Boris, what is the formula using a Boltzmann entropy? How would you express the number of states?
Omega, big omega E.
That's what, W is the partition function. No, in terms of this quantity.
Exponential.
Exponential, yeah.
S over K.
S over K. Yeah, so let's recall that S equals KB, okay, without subscript for brevity, KB logarithm of omega, right? And then omega equals S over K to the power E, right? Now, which S?
S is the entropy you can use.
Yes, this one, right?
Yeah.
But then substitute our expansion. Who has not? Kyrell. If you substitute the expansion of entropy, this one, in the formula that Boris has now suggested, what do we get?
E raised to S.
To S
Minus partial of S.
Yes.
With respect to E.
Or epsilon.
Epsilon, sorry. Times epsilon all over, or times 1 over K.
Okay. Dionessa, what is ds over d epsilon? Hello, Dionessa, are you able to connect your microphone to? So yesterday we used this definition, entropy, derivative of entropy with respect to energy. What it is?
Is it the temperature?
Yes, almost. Yeah. By the way, I'm sorry. I've noticed after the lecture that in the very last slides I used that it's temperature, but it's not temperature. It is 1 over temperature. Okay. Then we go here to write. Do you see this angle of the whiteboard?
Yes.
Or is it already too low?
It's okay.
It's okay. Very good.
It's okay.
So we have e to the power s over k. I factor out the exponential minus epsilon k over, oh, sorry, epsilon, epsilon over kt, right? And everything was correct? Please check me. All right, very good.
Excuse me.
Yes?
How we find a partition function to be e power s over k b?
This is, you remember last time we introduced the Boltzmann definition of entropy, k logarithm b. Now from this equation, we find that, so if you solve this equation s equals k logarithm of w, logarithm of w is s over k, and w is e to the power s over k. Is it right?
Yeah, thank you.
Then we used expansion, a Taylor expansion of entropy, and write this expression. Okay, now I will need a new page, of course. And so we found now that w of e minus epsilon is equal e to the power s of e over k times e of epsilon minus epsilon kt. Okay, now note that this is a constant, right? E is fixed, s is a function of e, but since e is fixed, this is constant. K is constant, so this is just a constant. So this term is not variable, does not depend on epsilon. Here I forgot the second. So all the dependence on epsilon is in this term. And this term, by the way, has bears often the name of Boltzmann factor. I always forget Boltzmann is with one n, right? It's spelled with one n. Who remembers?
I guess it's 2n.
2n. Yeah, can one check? Because
it's 2n.
Huh?
2n.
2n, yeah, because there are various names like Tuckerman, for instance, is 1n, Boltzmann is 2n. Very good. I trust you, it's 2n. Okay, Boltzmann factor, it's exponent to the power minus epsilon kt over kt. Okay, and now I want to ask you how we find the probability of finding configuration, macroscopic configuration, in which the heat reservoir has energy E minus epsilon, and the system of our interest has epsilon. Idris, can you?
Yes, it's W of E minus epsilon of epsilon divided by W.
Exactly. Okay. Okay, and how do we find W E?
By integration.
Integration of what?
Of the W. Yes, so it's.
Yes, very good. With respect to?
DE.
DE?
Yes.
What do you mean by E? Capital or lowercase? Epsilon. Is it epsilon or E that you must integrate it with respect to?
It's epsilon because E is.
Okay, let me ask the limits of integration from to?
From 0 to epsilon.
To epsilon?
Yeah, to E. It's the maximum.
To the capital, yeah.
Yeah.
Okay. So we found this. And basically, yes, this is, we can now substitute this formula, right? 0E times, times, okay, let me call this factor C, okay? C, d epsilon, by E epsilon over K T, okay?
Yes.
So we substitute here C, E minus epsilon over kt divided by c over integral 0 to e d. This one is epsilon e epsilon kt. Constant goes away. So at the end, this constant didn't matter at all. All right. And now you can notice that we basically expressed the probability of finding a given system is now. So this probability, if I recall that we have placed a constraint on number of particles, on volume, and so, okay. And yeah. So now energy can vary, but what we fixed, we keep fixed because the system is globally, the super system was at equilibrium. The constraint is actually now temperature, right? Epsilon is now a variable, but temperature is fixed because our system at equilibrium. So this is called Nvt ensemble, which is the slang for the canonical ensemble. So we have derived the expression for the of the probability of finding a system in a canonical ensemble. Again, this can be generalized to a way that our universe consists of many systems. So that's, you recall that the word ensemble, that there are many universes or one universe where there are many similar systems, all of which have the same number of particles, the same volume and temperature. Okay, is it clear? Does anyone has a question? Does anyone?
Can I ask again?
Of course.
So, from the Taylor expansion to the, when we plug in the expansion of the entropy,
yes,
the higher order terms, why did they?
Okay, so we pretended that the total energy E is a very large number. Okay, so we can in fact measure energy in units of total energy. Okay, so for instance, we say that epsilon is a small fraction of the total energy in the universe. Okay, so if the universe, our universe is very large, so there are like 10, I don't know, many orders of 10, then this epsilon is a very small number, right? And the Taylor theorem says that, okay, if you take, okay, epsilon is even 0.1, this number will be something like it will be 100. So it's such a small number that we may be happy with just approximate calculations, all right? Does that answer your question?
So if it becomes the exponent, it is negligible. So
you're asking what happens if it becomes non-negligible. Epsilon with respect to the whole system is very large, right? Well, then probably you better use microcanonical ensemble because if you would like to describe in this system the heat reservoir, you can. So in other words, this concept of canonical ensemble is useful when you consider a system connected to a heat reservoir, like I don't know. Again, I can see my video camera. If you see me with a cup of something, there is some liquid, right? And the energy that is in this cup compared to the energy of the whole room will be negligible. And so what we want to say, we want to measure the temperature of the room, and it is more convenient for us to measure temperature, not the energy. We don't have energy thermometer, right? well, probably there is some device that can give us some estimates of energy in some situations, but it is much more convenient to use temperature when there is a huge heat bath, heat reservoir around us. And of course, this concept will be useful in such situations when our system is connected with a heat reservoir. If you have a closed system, which is almost, I don't know, half of the whole of the super system, probably thermodynamics will not be accurate. So you can still evaluate this formula, right? But your error of your estimate will be larger. All right?
Okay.
So the ultimate goal of most of the numbers that physicists produce is not to give you, like number pi to the 99 digits. It's very often useful at least to get approximation. And for most of the systems, like water in a cup, such approximations are more than you ever want, right?
Mm-hmm.
So it's a matter already of practicality, okay? Other questions?
Yeah, I have another question. The probability we calculated is only for probability of finding only one macro state, yeah?
Yes.
Because it's not the most probable macro state still.
Yes, so here we actually, this expression is probability of any macro state, okay? But of course, in equilibrium, we expect that this system will be in the most likely in the most likely macro state. Yes, so both are true. So you expect to find it in the most in the macro state. So how would you find it? You could also try to find the maximum of this probability. Okay, we are not going to do this exercise, but in principle, yeah, you can find the most likely macro state too. But in general, we found the expression for probability in general as a function of energy, epsilon, and KT. And in fact, this is also very famous expression. So this is called Maxwell Boltzmann distribution, which says that the probability of of finding a state with a given energy is e to the power minus epsilon over KT. That's, of course, again, is only when you have many degrees of freedom. Okay, like inside your little system, there is still many ways you can fill this system with energy. And around this system, there is a huge reservoir, okay, like universe huge. And it is a matter of practicality to use temperature, because we can, so suppose the heat bath is our universe. It has infinite amount of energy, maybe, right? And so we can't even hope to measure this huge number. That's why it's more convenient for us to use temperature, okay? So temperature is what replaces for us the measurement of instead of measuring the energy in the whole universe, we just need to take a thermometer and to measure the temperature. Since we assume that our system is in equilibrium with, so this cup of water is in equilibrium within air, we can measure temperature by the zeroth law of thermodynamics, and that's all we need. We now have expression which gives us probability of any macro state. Okay. Other questions? No questions. So let me give you a bit more of terminology. So actually, this integral here, when we already canceled this constant c, this integral is called Zn of v of t is the integral of d epsilon e to the minus epsilon KT. Okay, it has a name. So you remember that actually the probability from the previous slide, the probability of finding epsilon is e to the power minus epsilon over kt divided by the integral of epsilon of minus epsilon kt, which is z n v t. Now, higher, what do you think we can call this number z?
I'm sorry?
How would you call this number z?
This is the probability, right?
Yeah, so this is, the probability of finding epsilon is e to the power minus epsilon divided by kt and divided by the normalization constant. And normalization constant is actually the integral of this e to the minus epsilon over kt. So by analogy with something that you already, that we already have discussed, how would you call this function z of nvt?
These are the total, like this is the ensemble because
Well, yes, we are in the canonical ensemble now, which is probability of finding macro state. Who has
a partition function?
Partition function, right?
Yeah.
Last time, I think Dionesa was asking me about partition function. Anna was maybe too. This is the canonical partition function. All right. Let's just recall that the microcanonical partition function NVE, yeah, it was well, the integral of delta function over h xp minus e dx dp. Yeah, that's all right for now. Okay, let's take a little break. Where do we? Where are we right now? 5:04. Okay, yeah, let's take a little break now. It's 15, and yes, someone already the late minutes. You can continue. All right. We will miss you, Idris. Okay. We begin. Everyone is here. I hope.
Yes.
Okay. Yes. Except Idris. All right. Distraction can occur. All right. What I wanted to tell you in the following. So far we defined this partition function as for energy. So we basically have found the way to represent the probability of a macro state given of a given energy. Now I want to, but when we studied the function of
You are muted.
Okay. Again, we have defined the microcanonical partition function as an integral. By the way, I forgot 1 over n factorial here, as an integral of phase space variable x and p, right? You see, and here we have an expression for the canonical partition function as an integral of epsilon, which is the energy of the system of interest, right? How to make it? Does anyone knows how to express the partition function? A way to cast the partition function in the form of as the probability of a collection of microstates. So I want to represent my partition function actually as dx dp, as a integration in the phase space, not in the space of energy. Any ideas? How would you do that?
you change the
You
energy.
have to use the density of states.
So density of states. Well, okay. Let's go like that. So how I do that? So a probability. Okay, probability of the probability of. So the probability of a given energy is proportional to e to the power minus epsilon over kt, right? Then we also agreed that it's also the number of microstates that can realize this epsilon, right?
Yes.
Okay. Then how can I calculate the number of states that realize it, or realize this? So I can do this by integrating with respect to d epsilon times something. Now I want to tell that epsilon, so I want to find a mathematical way to tell that epsilon is equal h of x of p. How would I do it? Any ideas?
Can you repeat the question, please?
So now I want to multiply this integral by something that will mathematically convey the idea that epsilon is h of x times p. No, okay, it's the delta function. Okay, delta function is very often used in statistical calculations to express the idea that this epsilon, I really mean to be equal hxp. And then this integral, what I will get, Kyrell, what is, can you integrate this?
That, sorry. That
Can you take this integral? It's e to the power minus,
e raised to negative epsilon.
I'm integrating over epsilon.
H of xp over kt.
Over kt. Okay, and now actually the partition function can be written as integral over dx dp of e to the minus h xp over kt. Sorry. Okay, let's make, I'm writing again. So as at Nvt can be recast as integral over dx dp over e to the minus h x. Okay, just that now you can see that this expression here with delta function is a lot like expression here with the exponential, right? And one was giving us the partition function of the microcanonical ensemble. Now we have the partition function of the canonical ensemble. Okay, and you remember, so we have very nice definition, interpretation of, due to Boltzmann, of what is the logarithm of microcanonical partition function. It is entropy. And who knows what is the logarithm of the canonical partition function is related to?
Yeah, between this KB equals to KB.
KBT, so this is for microcanonical, okay, a partition function, it's entropy. Now if I take logarithm of the canonical partition function times KBT, who knows what it is in thermodynamics?
The name?
Name of this thing, yeah. It's a very useful physical quantity. thermodynamic quantity.
Heat capacity?
No, heat capacity is a derivative. Actually, you can obtain from this thing heat capacity.
Heat.
Huh?
Heat.
KT?
Heat.
He
Again,
said
Boris.
heat.
Heat?
Yeah.
Heat, no, no. Okay, let me call it A. It is called Helmholtz free energy. But this is the statistical mechanical definition of who knows how in classical thermodynamics one defines the Helmholtz energy. Does anyone know? So all these operations, when we were deriving and playing with the definition of entropy, it was just a very hidden way to do what is called, so it's a different path to doing what is called Legendre transform, just in case you have heard of it. But basically we had, right, E, energy in thermodynamics, right, D, E, the change of energy was T times ds minus, let me put it just dV, okay? And what we do to define A is we take E minus T times S, okay? This is the definition of Helmholtz free energy. And so that dA is dE minus dTs. We use the product rule of, because dE we leave as it is for now. And there are two variables, temperature and entropy, dT plus T ds, okay? And now substitute the expression for dE over here and tell me what is the answer. Someone do this substitution and give me the final answer. This is a little exercise for you right now. I did a mistake, by the way.
Yes, there's a mistake. It won't
Yes.
cancel out.
Yeah, I forgot. I put, this is it. Kaya, you have the final answer?
Yes, I'm typing it in the chat.
You wanted to type it in the chat? Yeah. Tell me when you do something in the chat, otherwise I can see.
Okay, just a minute.
Idris is back, I see, but I'm sorry, my computer is really small. I have a very small screen. That's why I all the time struggle freeing some space to be able to write on the whiteboard. dA equals minus dW, sorry, minus S dt. Okay, so almost with sign I have a problem. Why there is minus and parentheses? Okay, so let's do it together. TdS minus dV, that is energy, and then we had these two terms, right? dTs minus TdS. Okay, this will cancel, and we have yes, sorry, that's all right. Then you are correct. Sorry, your expression is correct. Very good. All right. Is it clear? This little derivation. Okay, so what happened now? Now you can, from this expression, you can see that dE over, oh, sorry, d dA over dt is equal what? Anna, what is dA over dt? So this is dA, partial derivative of free energy with respect to partial derivative of the temperature.
Minus S.
Minus S, okay. And you see that what we did before in the microcanonical ensemble, or when we were considering internal energy, we had, you remember in the first law, to introduce this fancy variable entropy, which at the time when it was introduced, it was really a progress. But again, I repeat, it's a little funny because it was a quantity that by definition should have explained everything what was not what the theory could not account for at the time. Okay, and then right now we have changed to change the independent variable from entropy to temperature, and this is indeed very convenient because I don't know how to measure entropy, but all the thermodynamic systems we usually use a temperature, right? We use thermometer, and how to measure temperature, it is pretty clear and is convenient. So canonical ensemble, in fact, is a very convenient way to address problems in thermodynamics, not microcanonical ensemble. And one reason is that I mentioned before, we cannot measure energy in the universe, all right? And therefore, instead of energy in the universe, we can, or in the heat reservoir, we can use temperature, which is clear how to measure. And there is actually always a distinction. So we also call energy, number of particles, and volume are often called, do you see what I write? Or is it
No,
too?
sir.
These
Yes.
are called extensive variables, okay? The reason they are called extensive is that if I have one system, for instance, with energy E, and I add another energy, another system with energy E, in the total system, we have energy 2E. So they are extensive. We extend in system, we also extend the quantity E in a way, right? And in principle, to construct universe, we would count how much these systems, legal systems we have in the universe, okay? There are intensive quantities which are intensive quantities, Dionessa. So if these are extensive quantities, because by summing two systems, we extend also the quantity of energy, number of particles. So what would be intensive quantities? It is some quantity that if you take one system with this quantity and another system with this quantity, when you sum them together, so you connect this system as a one system, this quantity does not change. Dionessa?
The quantity in the for each system?
Yeah, so there is a quantity that, like before, extensive quantity, right? Energy is extensive quantity. So if I had one system with energy E and another quantity, another system with the same energy E, if I connect these two systems in one, I doubled the quantity E, the energy. The same would be for number of particles. If there was n particles in one system and n particles in another system, in the system consisting of these systems together, there would be 2n particles. Same goes for volume. But now, do you know quantities that if there is this quantity Q in this system, quantity Q, it's not heat, quantity Q in this system, and we have a system consisting of these two subsystems, the quantity Q remains the same.
Is it temperature?
Temperature, right. So you remember 0 to another, yeah, other quantities like that, like temperature. You can continue. Okay, you
pressure?
can pressure, right? Pressure.
But
Another
only
quantity.
for certain systems.
Certain system in yes. Which systems? Can you tell me? Systems in equilibrium. Okay, that's one when you can have temperature or pressure, because again, I remind you this example. We had gas over here and eliminate this compartment. Gas starts to expand. While it expands and until it comes to the most likely state, there is no thermodynamic temperature. There is a way to define temperature, but no thermodynamic temperature or pressure. We don't know what these quantities are until the system equilibrated. And when it equilibrates, pressure and temperature will be different from what was in the confined gas. Okay, but in equilibrium systems, yes. So if you have half system and another half system, if here there is temperature, the same temperature will be here. Same goes for pressure, because if the pressure would not be equal, the wall, for instance, would start to move under the pressure. Okay, systems must be in equilibrium. Then there is temperature, pressure, and one more quantity we have discussed. Dionesa, can you? Just one more quantity.
Entropy?
No. Chemical potential we mentioned in the first. In the second, yesterday actually, I think yesterday we mentioned the chemical potential. Okay, so these quantities are actually very convenient because, you know, we cannot describe what is the volume of universe, right? But we can instead of the universe, we can represent by another measurement of pressure, external pressure, right? We cannot describe how much energy is in the universe, right? It's a huge number, but we can describe, replace measurement of energy in the universe by another quantity, temperature. And same goes for the chemical potential. So we cannot count number of particles in the universe, but we can measure chemical potential. Okay, these are intensive quantities, okay? Questions? No questions. Okay, Kyrell, what kind of quantity entropy is? Is it extensive, intensive, or neither? Kyrell? You are connected. It's just tell me something if you need the seconds to think. So I'm here or something, because I really don't know what's going on. If there is a silence.
I think I had no idea. Sorry.
What? You have no idea. Okay. So you remember
Extensive?
who says this? Anna? Anna.
Yes.
Okay. Yes. Okay. Extensive indeed. So you remember when we defined entropy for microcanonical ensemble. So there was quantity W, and which was equal W1 in the one system, W2 in the other system, right? And we defined entropy through logarithm, because logarithm is such a nice quantity that what was product becomes sum, right? And
but is it always an extensive quantity?
No, it's not always, unfortunately. But there is I mean, one thing is that in classical thermodynamics, it is always. So it's actually today there is a branch of, well, to say, in the classical thermodynamics, people considered only such systems which had entropy as extensive quantities. There are systems in which entropy is not an extensive quantity. And this is called the so-called non-extensive, by the way, the word non, when you hear.
Which systems are those in which it's not an extensive quantity?
So usually one assumption that we used implicitly, with thermodynamics, one thing that is always very difficult, that you see equation like first law, but there is a lot that is not written in the equation, and people often make subtle mistakes because they forget all the context of that equation. One is that a real system, okay, let me put a glass of water, okay? In a real system, okay, this water, it interacts with air, and let's say a particle in the air gives a potential of on the potential energy. There is potential energy due to interaction of particle in the air and particle in the liquid. Okay, but because the systems is so large, this distance between particle is tiny. So it's some distance dr, which is negligible. Okay, and the potential is usually between this particle would be actually energy of dr would look something, okay, this is dr, it could be huge at small distances like angstroms, for instance, but then it decays very quickly. Okay, and therefore, well, there is some energy due to interaction. So there is some energy that occurs at the boundary between liquid and air, and there is actually a branch of thermodynamics that is occupied with the so-called surface effects. So at the surface there are interesting things that happen, but to see such effects you need really very refined devices. With usual thermometer that we measure air in the room, you can detect such things. So how extensive system happen in physics, because there are interactions which are very long range. When this does not decay very quickly but remains of a long range, the potential does not decay in zero. And then we cannot neglect interaction between the heat bath energy of the small system due to all particles very far from the system. They will add some energy contribution, and dynamics of this particle will be very much affected by these particles far away. All right, so it's very difficult to define what is actually the boundary of the system, what is the volume, because part of energy of the system is actually due to many particles which are outside from the system. All right,
Yes. Thank you.
Such systems occur. It's an interesting branch of and complicated branch of thermodynamics and a field of active research today. It's an interesting question, but it's outside of the classical statistics, statistical mechanics. That's why it's rather considered a fancy system, exotic system in the context of a course of statistical mechanics. Okay. Yeah, but yeah, for most of the time, especially when you don't speak about, when you speak about information theory, it's usually all right to assume that entropy is extensive quantity. Next time I'll show how the properties of the logarithm of the canonical partition function coincide with the Helmholtz free energy. Right now, just one little demonstration. Two-level systems. Who has not read the home assignment? Please tell me, because if everyone read, that will be much faster to discuss two-level systems. Everyone has read? Said, have you read?
Which assignment?
So I asked, and I have sent you an email to read about two-level systems, section in notes that were attached also to that email.
Okay, unfortunately, I haven't paid much attention.
Why?
Doesn't
it deserve your attention?
No, that's not true. I was completely in the mathematical physics course, and
all right.
Okay,
Ivana, have you read the home assignment? The home assignment. No.
Yes, but
Yeah?
it was a little faster. I didn't pay too much attention to specific topics, and I read the questions quickly, but maybe
Okay.
I can
Okay.
understand.
All right. So two-level systems. Imagine we have one in 1D, okay, system where each box is a particle, okay, impurity, as in this lecture notes. And then the particle can get excited, and then it could be excited. This particle is empty, it's not excited. Another impurity can get excited, and then not excited particle have, so the total we have n particles, and out of n particles, there will be n1 particles excited. Excited particles have energy, each of them has the same energy, epsilon, okay? For that reason, the total system would have epsilon times n1. The energy of the total system would be epsilon times n1. Okay, so this is quite a simple system. And in the sections, in the section of the notes, you can find various formulas derived for the system using the microcanonical ensemble. Do you see now my screen? Okay, very good. All right, so you remember there is we import some packages with functions that are very useful in the code below. We don't need. So I executed this code already to import. Now we'll have n is capital N in the section is the number of impurities here. Okay. Then I apply, I number all cells. So I number all impurity in this figure that I showed you on the whiteboard a moment ago. I can enumerate each figure. So you see that I use variable e in range from, so e runs from 0 to n minus 1. That's why I need to add e. To E, I add 1 in order that cells would have, it would be an array numerated like 1, 2, 3, 4, up to 6. S equals, yes?
The cell is used to label the cells.
Yes, so yeah, I forgot to mention this. Okay, let me switch back to whiteboard. Okay, here, this. So this N, capital N, was in the Cardar's lectures. Here we have capital N, and each cell is numbered. So there is 1, 2, 3, 4, 5, 6, 7. Okay, right now there are 6. And I will use a definition. There will be number S. Okay, S is a number that separates subsystem. So there will be a subsystem. For instance, if S equals 4, then 1, 2, 3 are cells that are inside my subsystem of interest, and the rest will be in the reservoir, so to speak, or in the second subsystem, as you like. Clear?
Yes, sir.
Mm-hmm. Now I switch back.
Before going, sir.
What?
So, before going, the capital N are the number of particles.
So right now, yeah, because you see, the usually programmers have there is already such tradition in programs in Python, at least, to use variables with a lowercase letter, to name variables with the lowercase letters. Capital case letters usually refer to a class. Oh, well, you will probably learn in Python if you haven't yet what a class means, but yes, that's why I use little lowercase n, okay, not capital. So this is n, number of cells, okay. So n is this, is the maximum number of cells. This is the number of cells. S is the number, so if S equals 4, means that every cell that is less than 4 is inside subsystem. Okay, clear?
Listen.
So I now want to share back to Firefox. Okay, now we are back to Firefox here. Cells, I numbered cells 1, 2, 3, 4, 5, 6. I selected half of, so cells 1, 2, 3 is in my subsystem of interest. The other subsystem is of less interest. Okay, K. So K is the energy. Okay, here I use letter K. Why I use letter K? Because this system, if you think of it, it resembles the egg carton problem, right? In egg carton problem, I had 6 cells, but I just arranged the cells in 2 rows. Right now, I put all the cells in 1 row, but that's why I chose K. But in principle,
So didn't S, like, if N are the total number, N are the total number of particles? No, total number of.
Oh, okay. N is total number of particles. If you wish, it's a total number of cells. If you want to interpret it as a carton egg, as an egg carton problem, okay?
Okay.
Yeah. The fact that
is
what?
What is S then?
S is the to separate cells that are in the subsystem. So all cells that have number less than S are in the subsystem. In the subsystem of my interest, okay?
So N minus, no.
N minus S will be the other part of the whole system. So the super system consists of 6 cells, okay? If I put S equals 4, then cells 1, 2, 3 are in the first subsystem, okay?
Okay.
Okay. Because now I arrange my cells on the line, it's very convenient to define, it's a wall, where the wall is, okay? When we defined super system, we had placed a wall to separate subsystem 1 from subsystem 2. So S is the wall, basically, okay? The coordinate of the wall. So now I sample a configuration. So what I do, I say NumPy, the package NumPy here, to get me a choice of cells, numbers 1, 2, 3, 4, 5, 6. Just give me a choice of size K. In other words, I ask to place in the cartoon 3 particles. So give me the cells, numbers of cells where the particles are, right? Randomly. Replace files means that if a particle already occupied 1 cell, the second or third particle cannot go into the same cell. Okay, and you can see how it works. So I run. You see that system energy is 3. The whole system, in parentheses, I put the value of energy. It's fixed by number K. And the cells that have been selected by the particles are 3, 4, 5. Okay, that means that in subsystem 1, I have 1 particle in cell number 3. Cells number 1 and 2 are free. Subsystem 2 has particles in the cells 4 and 5. And therefore, it has energy 2, whereas the first subsystem has energy 1. Now I can run this code again, and you see the numbers have changed because right now there is 0. All particles have gone in the second subsystem. 0 energy in the first subsystem. So that shows you that it's some randomly chosen configuration from microcanonical ensemble, by the way. Is it clear? Questions? No questions. Now I show you one trick, okay? If you haven't used yet random numbers, random number generators, random number generators are functions, and if you like, in the Python language, that give you a sequence of random numbers. So it's a mathematical function that knows how to find a sequence of numbers, which obeys a given probability distribution. But in principle, all the sequences, they are enumerated, and I can select that, give me a sequence that has label 0, so to speak. In language of generators, it's called usually seed. Basically, you give some number, like for instance, now when I was generating number, probably the seed was taken as the time at the moment when I called the function. It was taken as a random number to seed as a seed of sequence, randomly generated sequence. Right now, I fix 0 is just, I fix the sequence so that when I run this, again, I take a sample size. Now I take 3 choices, and you see there are 3 choices of cells in the systems. These are 3 members of microcanonical ensembles, okay? But now if I run this code many times, the sequence will not change because it is randomly chosen configurations, but because I fixed my random sequence to a certain value, these randomly generated numbers will be always the same. And now to make the histogram, I will sample not 3, but 100,000. So I will take 100,000 configurations, and then I will use histogram. I hope you know what is a histogram. Is a numeric means to estimate the probability density. Right now in this system, I sample the energy in the first subsystem. So it's energy in the first subsystem. And you see that most of the time there will be 1 or 2 particles in my subsystem. And very rarely all the particles will go in the second subsystem. Let's see what happens when now I make my cartoon egg to have egg cartoon, to have 10,000 particles, okay? So what did I do in terms of 2-level systems? I take a system that consisted of 10,000 impurities, a very large number, right? Not Avogadro number like molecules in the mole of gas, but still a lot. I need to create 10,000 cells, and I again divide my systems in half. So there is the first 5,000 of 10,000 total cells will be in my subsystem, and in the subsystem which I don't care about at the moment, the second subsystem, there will be also 5,000 cells. And I also increased the number of energies to 3,000. Okay, let's run it. It will take just a little longer because it's already, instead of 6, now instead of 6 cells we have 10,000 and 5,000 in subsystem. So the histogram will show you the energy in the histogram will show the energy in the first subsystem when it finishes calculation. All right, while it's calculating, what I will want you to do is that I want you to use one home exercise. Actually, it will be exercise number 2. Exercise number one will be a little simpler. Exercise number 2 is that you apply theory of canonical ensemble that we derived to describe the temperature of the system. You tell me the temperature of the subsystem with 5,000 particles, but you also will calculate for me the chemical potential. Okay, that is what I would call here chemical potential, right? In the subsystem, there will be right now there will be S cells, right? So what happens if I decrease number of cells in the first subsystem by little number dn, right? ds, okay, or increase? What will happen with the chemical potential? All right.
Can I ask? I thought for this the size is k. Is it?
No, the K is number of excited impurities in the language of the nodes. It's the number of particles in the egg carton.
Okay.
But the number 5000 is the number of particles in the subsystem 1, which is
Okay.
subsystem of my
I
interest.
understand.
The total number of whole particles in the supersystem is 10,000, okay?
Okay.
Now I have the histogram, and you see in the histogram is already much more sensible. So you see that we have split our system in two halves. And what would you expect? Half of energy, most likely state, is when half of the system has half of the energy. So the energy in terms of equilibrium thermodynamics, out of 3,000 units of energy, 1,500 will be in the subsystem of interest, and this will be the most likely value. And sometimes you could observe values which are very close. How much? 1,500 plus minus 22. Standard deviation is also computed numerically here. It is 22, okay? And that is a very small number. Observing here 0 particles is almost impossible, okay? But here we observed a system which is 10,000, okay? 10,000s of particles, right? The uncertainty divided by the value of energy, so the uncertainty of energy in subsystem divided by value of energy is very small. In other words, what I'm trying to say is that if you have such a system with macroscopic measurements, you would not be able to see such little changes as 22 energy units, okay? So you would see a large number like 1,500 with your macroscopic device. And this would be just a value that is sort of accuracy of your measurement tool. Here we had only 10,000, but in thermodynamic systems, we have like Avogadro numbers of molecules. It's a huge number, which is difficult to interpret. Okay, just to show you that when I start to decrease, so let's decrease number of particles by 10, and energy also by 10. That calculation will be a little faster, but you will see that as I decrease the size of the system, then the uncertainty will become larger. The opposite limit, which I cannot, you see, now we have 150, almost average energy, the most likely energy in the system, in the subsystem, and 7 is the uncertainty. But 7 divided by 150 is already a bit large value. So uncertainty with respect to the value of interest increased. The opposite limit, of course, I cannot show because we will stay here all the evening waiting when, let's say, 100,000 of particles are simulated, sampled. But what this example should show is that when you increase number of degrees of freedom, your peak here will become larger and larger, and in the limit, and it is often called the thermodynamic limit of large system size n, you would obtain a delta function. That's what we see when doing macroscopic measurements on substances consisting of large, like almost infinite number of molecules. In principle, in statistical physics today, one of the branches of statistical physics is the study of fluctuations. Fluctuations is actually when you have already modern devices that allow you to measure quantities in a very small systems. Today, technology allows really precise measurements. Then you start to see actually that at certain time you attempted a measurement, you got one value a little bit less. At another time you measure on the same system the temperature, and you see something different. These are called fluctuations, and one of the modern branches of statistical mechanics is a study of these fluctuations. But in the classical thermodynamics, the fluctuations are ignored because the systems are so large and these fluctuations are so small that with the tools that were available at the time when thermodynamics was developed, such deviations were not too little to be detected. Okay, do you have questions? Or are you already sleeping?
What is the homework again?
Okay, the homework. The homework, I'm sorry, may I just ask for a little more time? We are almost done with our time, okay, if someone needs to leave, please leave. But I want to explain you just a little simpler example. This that will be a first homework exercise. In this little simpler example, what is simpler? It's first I wanted to show you the same. I show you that it's the same 6 cartoons, but what I change is that now particles can go into the same cell. All right. That changes number of possible configurations, but makes actually the problem much simpler. These are all the same exercises. In principle, the results of this experiment will be, you see that with 3 particles in 6 cells, probabilities a little bit change. So the 0 value of energy has become now a little more likely, because there are more opportunities for the particle go into the subsystem that has been already occupied by other particles. The central value of energy a little more probable than the marginal value of 2 units of energy. And so this system is a little simpler, that impurities now can be excited not to first level of energy, but as much as you like. And the homework will be, so I want you in the first, let me share back whiteboard. So in the first homework, so exercise 1, okay, in the exercise 1, you have this system of n cells, okay, with the cell S, and upwards this is subsystem 2, okay, subsystem, okay, Roman number 2, and this is subsystem Roman number 1. So in this simple system, the particles now can go into the same cell. Particles can go into the same cell. Okay, find so S right now is, so we divided the particles can be 2, the total 4 and 6, in order that you could divide the system exactly in 2 equal parts. Okay, so in principle S will be always fixed to n over 2 plus 1. Okay, so the 2 subsystems have equal sizes. I want you to find the probability that subsystem 1 has energy epsilon, okay, in our case. So that probability that we excited some cell in the first subsystem k times, or some cell or so different cells, doesn't matter. So, energy, let me call it, okay, let me call it this way. So probability that with label 1 is that energy of the first subsystem is equal k. This can be quite easily found in terms of k and you can easily find the exact expression. Okay, but then I would like you to find entropy, entropy of this system, temperature, and finally the chemical potential. Okay, here in the system we volume, sort of volume and number of particles is the same thing. You can say that n is actually the volume and you excite some energy level in this volume, right? So the work term basically has form of or chemical or usual thermodynamic work. ST mu, okay, that's what I would like you to find in this first exercise, okay? Now, in the second exercise, you will use the two-level system. Two-level means that it is not possible to excite the same impurity more than one time. That problem will be already a little more difficult, and for that problem I only ask to find you S, T, and mu. Okay. Questions? Hi, you want to ask something? Hello?
So, sir, so we have a number of particles.
Mm-hmm.
We have two subsystems.
Yeah, of equal sizes, yes.
Equal size. And we need, for the first homework, we need to calculate the probability. So the first subsystem has an energy K.
Yes.
Okay, so we're gonna do the same for particles for 2 and 4 and 6.
So n, I want a general expression. In the first problem, I want a general expression. Doesn't matter what is n, is just such that it's even number, right? So that you could divide it into, okay? And actually,
go randomly to one of the cells.
Yeah, actually, you can also, okay, in addition, just to find an exact values in terms of n, yeah, I will ask you to take the limit of n go into infinity, I think. No. No, okay, I will not use it, but just as additional exercises, optional. You can try to use Theorem formula in some smart way, like in the notes Kardar does, to give me some interesting formula for entropy, if you like. For now, just, yeah, calculate in terms of n and k, what is the probability of finding K energy excitations in the first subsystem, okay?
The particles aren't distinguishable.
Particles are indistinguishable, and yes, and yes, but they can, in the first problem, they can excite, go into the same cell, okay?
Yeah, okay, I understand. So we can even have all the particles in cell number 1.
Yeah, we can have 2 particles in cell number 1.
And we can have nothing.
Huh?
And we can have nothing. I mean, no particle in this first subsystem.
Yeah, also we can have. And I want just general expression for K.
Yeah, general expression.
Finally, two-level system is a second exercise. It's basically the same questions, but now only one impurity can be excited at a time. So sorry, impurity or just one particle goes into cell. If there is already a particle in the cell, you cannot place any other particles inside. All right.
So wait a minute. So in each subsystem there are many cells.
N cells. Yeah, you can also, is an optional exercise. Yeah, consider various
the number of cells is the number of particles.
Mm-hmm. Yes, cells is number of particles. That's what you would use as a measure of to use that. This is the value you can use as to define the chemical potential. Okay, in this problem there is really something you can define as a chemical potential, which is some sort of work, which is the work associated with moving the boundary of the system. Okay, so making one subsystem larger and the other smaller, or vice versa. With that, you can associate an intensive quantity that let's agree to call chemical potential. All right, other questions? Okay, I think everyone is sleeping already. So thank you for your attention, and see you tomorrow at 4:15.
Thank you.
Thank you.
Thank you very
Thank
much.
you.
Thank you.